Right now, as you sit here, something is passing through your body. Not air, not light, not sound. Something else entirely. Hundreds of particles, maybe thousands, are streaming through your skin, your bones, your organs, every single second, and you will never feel a thing. They do not bump into your atoms. They do not scatter off your molecules. They pass through the walls of your home, through the bedrock beneath your city, through the molten iron core of the Earth itself. And they keep going, out the other side, back into the void of space, as though you and the entire planet simply were not there. These particles, if they exist in the form scientists suspect, make up the vast majority of all matter in the universe. Not 5%, not 10, roughly 85%. The stars you see when you look up at night, the planets, the nebulae, the great swirling galaxies captured by the Hubble and James Webb Space Telescopes. All of that visible matter, every atom of hydrogen and helium and carbon and iron, everything that has ever been measured or touched or tasted by any living thing, is the minority, a sliver, a thin luminous skin stretched across a vast and invisible body. We call it dark matter, and for nearly a century, it has been the single most frustrating mystery in all of physics. But in late 2025, something extraordinary happened. A lone astronomer at the University of Tokyo, after sifting through 15 years of data from a NASA space telescope, announced that he may have finally caught dark matter in the act, not inferred it, not calculated, not modeled it, seen it, or at least seen the light it leaves behind when its particles crash into one another and annihilate in a flash of gamma radiation. If he is right, it would be the first time in human history that dark matter has been directly observed. It would confirm one of the most popular theoretical models for what dark matter actually is. It would mean that a new fundamental particle, one not included in the standard model of particle physics, is real, is out there in incomprehensible quantities, and that the invisible scaffolding holding our universe together has finally stepped, however briefly, into the light. If he is wrong, well, it would not be the first time a promising signal turned out to be noise. The history of dark matter research is littered with false starts and near misses, with tantalizing hints that dissolved under closer scrutiny. The scientific community has learned to be cautious with claims this big. Extraordinary discoveries demand extraordinary evidence, and not everyone is convinced. So tonight, we are going to tell you the full story, not just the new discovery, the whole story. We are going to go all the way back to the beginning, to the first clues that something was missing from our picture of the cosmos, clues that appeared in the 1930s and were promptly ignored for 40 years. We will meet the eccentric Swiss astronomer who coined the very term dark matter and spent his career being dismissed by colleagues he openly insulted. We will meet the determined American scientist who proved dark matter was real, who faced institutional sexism at every turn and responded by letting her data do the talking. We will follow the generations of physicists who have been chasing the invisible ever since, building detectors in abandoned gold mines a mile underground, launching space telescopes into orbit, smashing particles together at nearly the speed of light in tunnels beneath the Swiss countryside. We will examine the evidence that has piled up over 9 decades, from the rotation curves of spiral galaxies to the cosmic microwave background radiation, from the collision of galaxy clusters to the vast web of filaments that connects the largest structures in the observable universe. We will explore the leading candidates for what dark matter might actually be made of, from massive particles interacting through the weak nuclear force, to ultralight quantum waves, to microscopic black holes left over from the Big Bang. We will look through the eyes of a space telescope that sees the universe not in visible light, but in gamma rays, the most energetic form of radiation in existence. And we will examine the new data, the new claim, and the fierce debate that has erupted around it. You might be wondering how scientists can be so confident that something they have never directly detected actually exists. It is a fair question, and it gets to the heart of how science works. We do not always need to see something directly to know it is there. You cannot see the wind, but you can feel it on your face and watch it bend the trees. You cannot see gravity, but you can watch an apple fall and measure the trajectory of a thrown ball. You cannot see the magnetic field that surrounds a bar magnet, but you can scatter iron filings on a sheet of paper and watch them snap into the invisible field lines. Dark matter is like that, only on a cosmic scale. We see its fingerprints everywhere we look, in the spin of galaxies, in the congregating of galaxy clusters, in the pattern of the oldest light in the universe, in the bending of space-time around massive objects. We see the trees bending. We feel the wind on our faces. We just cannot see what is blowing. And that is what makes the new result from the University of Tokyo so provocative. Because for the first time, a scientist claims to have seen not just the wind's effect on the trees, but a faint glimmer of the wind itself. A glow of gamma radiation that could be the light produced when invisible particles destroy each other in the dense heart of our galaxy's dark matter halo. If confirmed, it would transform dark matter from something we infer to something we observe, from a shadow to a signal, from a mystery to a measurement. This is the story of the invisible universe, and of the moment we may have finally glimpsed what hides within it. Settle in, get comfortable. This is going to take a while. To understand why this discovery matters, you first need to understand just how much of the universe we cannot see. And the numbers are humbling, to put it mildly. Take everything you have ever known, every mountain, every ocean, every skyscraper, every grain of sand, every drop of rain. Zoom out. Take every tree and every animal and every microbe on Earth. Take the Earth itself, the moon, the sun, all 8 planets and their moons, every asteroid and comet and speck of dust in our solar system. Now zoom out further. Take the Milky Way, all of its roughly 200 billion stars, all of its gas clouds and dust lanes and stellar nurseries. Now take every galaxy in the observable universe, all 2 trillion of them, each containing billions or hundreds of billions of stars of their own. Take all the gas between galaxies, the hot plasma in galaxy clusters, the wispy filaments of hydrogen that thread the cosmic web. Add it all together. Every atom, every photon, every bit of matter and radiation that interacts with light in any way. All of it, the entirety of what we call ordinary or baryonic matter, accounts for roughly 5% of the total mass and energy content of the universe. 5%. That is it. Let that sink in for a moment. Everything you have ever seen, everything any telescope has ever photographed, everything that has ever emitted light or absorbed it or reflected it, makes up 1/20th of what is actually out there. The remaining 95% is divided between 2 phenomena so poorly understood that scientists named them not for what they are, but for what they are not. About 27% is dark matter. The remaining 68% is something even more mysterious called dark energy, a repulsive force that appears to be driving the accelerating expansion of the universe, pushing galaxies apart at ever-increasing speeds. Dark energy is its own profound puzzle, one that Nobel Prizes have already been awarded for discovering. But tonight, we are focused on dark matter, because dark matter is the invisible glue. It is the unseen framework upon which the entire visible universe is built. Without dark matter, galaxies would not hold together. The stars at the outer edges of spiral galaxies, like our own Milky Way, orbit so quickly that the gravity of all the visible matter inside them is nowhere near enough to keep those stars from flying off into intergalactic space. Something else must be there. Something massive and pervasive and gravitationally powerful, holding everything in place like an invisible hand cradling a spinning top. Without dark matter, galaxy clusters, those vast collections of hundreds or thousands of galaxies bound together by mutual gravity, would simply fly apart. The individual galaxies are moving too fast for the visible matter alone to contain them. Without dark matter, the large-scale structure of the universe itself would not exist. In the first few 100,000 years after the Big Bang, dark matter began to clump together under its own gravity, forming a cosmic web of filaments and nodes. Ordinary matter, still ionized and coupled to radiation in those early eons, could not yet clump on its own. It was trapped in a tug-of-war between gravity and radiation pressure. But dark matter, which does not interact with light, felt no such pressure. It was free to collapse, to concentrate, to form the gravitational valleys into which ordinary matter would eventually fall. When the universe finally cooled enough for atoms to form, about 380,000 years after the Big Bang, ordinary matter found those dark matter structures waiting for it, like channels carved in a landscape, guiding rivers of gas toward the low points where stars would ignite, and galaxies would be born. Without that scaffolding, without those gravitational seeds, the universe would be a featureless, uniform fog of gas, with no galaxies, no stars, no planets, and no one around to wonder why. Dark matter shaped the universe. Dark matter built the universe. And yet, for all its cosmic importance, we have never been able to confirm what it actually is. We know a few things about it with reasonable confidence. We know it has mass because we can measure its gravitational influence. We know it does not interact with light because it neither absorbs nor emits nor reflects any form of electromagnetic radiation, which is why it is invisible to every telescope that operates across the electromagnetic spectrum, from radio waves to gamma rays. We know it moves slowly relative to the speed of light, which is why physicists describe it as cold dark matter. If it moved quickly, at relativistic speeds, it would have smoothed out the early universe rather than clumping together. And the galaxies we see today could never have formed. Computer simulations confirm this. Models with cold, slow-moving dark matter reproduce the observed large-scale structure of the cosmos with impressive accuracy, while models with hot, fast-moving dark matter fail completely. We know it is not made of any particle in the standard model of physics, the framework that describes all known fundamental particles and forces. Neutrinos, for example, are particles that barely interact with ordinary matter, but they are far too light and fast-moving to account for dark matter's behavior. Beyond these constraints, dark matter remains a blank page. We have theories, we have candidates, we have decades of experiments designed to pin it down. But until very recently, every attempt at direct detection had come up empty. And that is what makes this new result so electrifying and so controversial. But before we get to the new discovery, we need to go back, way back, to a time before anyone had even imagined that the universe might be hiding something from us. The story of dark matter begins, as so many stories in science do, with a single person noticing something that everybody else had overlooked. And in this case, that person was one of the most brilliant, abrasive, and underappreciated astronomers of the 20th century. His story is a reminder that great ideas do not always come packaged in great personalities, and that the truth of a scientific insight has nothing to do with how well its discoverer gets along with colleagues. Fritz Zwicky was born on February 14, 1898, in Varna, Bulgaria, to a Swiss father and a Czech mother. He grew up partly in Switzerland and was educated at the Swiss Federal Institute of Technology in Zurich, the same institution where Albert Einstein had studied a generation earlier. In 1925, Zwicky emigrated to the United States to take a position at the California Institute of Technology, where he would spend the rest of his professional life, and where he would make contributions to astronomy so far ahead of their time that decades would pass before the rest of the field caught up. Zwicky was, by all accounts, a scientific visionary of the first order. He proposed the existence of supernovae, massive stellar explosions, far more powerful than ordinary novae. At a time when the concept was entirely new, he predicted that dying stars could collapse into incredibly dense remnants made almost entirely of neutrons, objects we now call neutron stars. At a time when neutrons had only just been discovered, and the idea seemed ludicrous, he proposed that massive objects could act as gravitational lenses, bending and magnifying the light of more distant objects behind them. Decades before the first gravitational lens was observed, any one of these insights, had it come from a more personable scientist, might have brought its author fame and recognition during his lifetime. But Zwicky was also, by equally unanimous accounts, almost impossible to work with. He was famous for his volcanic temper and his contempt for colleagues he considered inferior, which was most of them. He reportedly called other astronomers spherical bastards, explaining with characteristic venom that they were bastards no matter which direction you looked at them. He feuded openly with some of the most prominent scientists of his era, alienating peers who might otherwise have championed his ideas. As science historian Stephen Mora once observed, conversations about neutron stars, dark matter, and gravitational lenses all tend to begin the same way. Zwicky noticed this in the 1930s. Back then, nobody listened. In 1933, Zwicky was studying the Coma cluster, a massive collection of over 1,000 galaxies located roughly 320 million light-years from Earth in the constellation Coma Berenices. He was analyzing data on the velocities of galaxies within the cluster, data that had been published by Edwin Hubble and Milton Humason 2 years earlier. What he found was deeply puzzling. The galaxies in the Coma cluster were moving far too fast. Zwicky used a mathematical tool called the virial theorem, borrowed from thermodynamics, to calculate the total mass of the cluster based on the observed speeds of its member galaxies. The virial theorem relates the kinetic energy of a gravitationally bound system, the energy associated with the motion of its components, to the gravitational potential energy that holds the system together. If you know how fast the components are moving, you can calculate how massive the system must be to keep them from escaping. Zwicky estimated the total mass of the Coma cluster based on the velocities of about 8 galaxies. Then he compared that figure to the mass he could account for by looking at the light output of those same galaxies, using Edwin Hubble's estimates for the mass of a typical galaxy. The numbers did not match. They were not even close. The gravitational mass of the cluster, the mass required to explain how fast the galaxies were moving, was roughly 400 times greater than the mass suggested by the light from its visible stars. 400 times. That was not a rounding error. That was not a calibration issue with his telescope. That was a gap so enormous it demanded an explanation. Either the physics was wrong, the measurements were wrong, or there was a vast quantity of matter in the cluster that could not be seen. Zwicky proposed the third option. The cluster, he argued, must contain an enormous quantity of unseen matter, matter that exerted gravitational force, but emitted no detectable light. He called it Dunkelmaterei, the German phrase for dark matter. In his 1937 paper, published in English in the Astrophysical Journal, he refined his analysis and discussed the problem at greater length, considering various forms that this invisible mass might take, including cool and cold stars, solid bodies of various sizes, and diffuse gas. It was a profound insight, and the scientific community largely shrugged. Part of the problem was Zwicky himself. His abrasive personality had earned him few allies and many enemies, and scientists, being human, were perhaps less inclined to take seriously a claim from someone who had called them names in public. Part of the problem was the sheer audacity of the claim. The idea that the overwhelming majority of matter in a galaxy cluster was invisible seemed, to most astronomers of the era, like a sign that something had gone wrong in the calculations, rather than a genuine discovery about the nature of the cosmos. And part of the problem was simply that no one else had the tools or the data to confirm or deny his results. In 1936, Sinclair Smith independently found a similar discrepancy in the Virgo cluster, calculating that it too contained far more mass than its visible galaxies could account for. But like Zwicky's work, Smith's findings were treated as curiosities rather than revelations. Zwicky's dark matter would sit in relative obscurity for nearly 4 decades, waiting for someone with better instruments and a more diplomatic temperament to prove him right. There is another figure who deserves mention in this early history, one who is often left out of the popular narrative. In 1932, a full year before Zwicky published his Coma cluster analysis, the Dutch astronomer Jan Uit was studying the motions of stars in our own Milky Way galaxy. Uit measured the velocities of stars orbiting near the galactic plane and found that there seemed to be more gravitational pull than the visible stars alone could account for. He concluded that the total mass of matter near the galactic plane must be roughly twice the mass of the stars visible in that region. This was a more modest discrepancy than what Zwicky would find in galaxy clusters, but it pointed in the same direction. There was hidden mass in the universe that did not reveal itself through light. Uit's work received even less attention than Zwicky's. His measurements were imprecise by modern standards, and the factor of 2 discrepancy he found could conceivably have been explained by populations of faint stars that had simply not been catalogued yet. But in hindsight, Uit was picking up the same signal that Zwicky and later Rubin would amplify into one of the defining discoveries of modern physics. It is worth pausing here to appreciate just how radical this idea was. In the 1930s, astronomers were still adjusting to the relatively recent discovery that the universe contained galaxies beyond our own. Edwin Hubble had only confirmed in 1924 that the Andromeda Nebula was a separate galaxy, not a gas cloud within the Milky Way. The concept that the universe was expanding had been established only a few years earlier. The notion of the Big Bang was still in its infancy. Against this backdrop, the suggestion that the majority of all matter in the cosmos was invisible was, quite literally, unbelievable to most scientists. It challenged a fundamental assumption that had guided astronomy since its inception: that what you see through a telescope is a reasonable representation of what is actually there. Zwicky was asking his colleagues to accept that the visible universe was a tiny fraction of the real one. Most were not ready. And so the idea waited, like a seed planted in dry ground, for the rains that would finally allow it to grow. That someone arrived in the late 1970s, and her name was Vera Rubin. Vera Cooper Rubin was born on July 23, 1928, in Philadelphia, Pennsylvania. She grew up in Washington, D.C., where she fell in love with astronomy as a child, spending hours at her bedroom window, watching the stars track across the sky in their nightly arcs. By the age of 14, she had built her own telescope with the help of her father, who also took her to meetings of amateur astronomers. She knew, with the unshakable certainty of youth, that she wanted to be an astronomer. In 1940s America, this was considered a peculiar ambition for a young woman. When she graduated from Vassar College in 1948 as the only astronomy major in her class, she applied to graduate programs in the field. Princeton University rejected her outright. Their graduate astronomy program did not admit women. That policy would not change until 1975. Undeterred, Rubin enrolled at Cornell University, where she studied physics under luminaries like Philip Morrison, Richard Feynman, and Hans Bethe, some of the greatest physicists of the 20th century. At Cornell, Rubin's husband Robert brought her a journal article by the cosmologist George Gamow, who wondered what would happen if you applied the dynamics of solar systems to the motions of galaxies in the larger universe. Rubin took that question further. For her master's thesis, she analyzed the motion of galaxies to determine whether their distribution in space showed any large-scale patterns. Her results, presented at an American Astronomical Society meeting in 1950, suggested that galaxies might be clumping together and streaming in preferred directions, an idea that was met with skepticism, bordering on hostility from the largely male audience. It would take decades for the scientific community to confirm that she was, once again, ahead of her time. Rubin earned her doctorate at Georgetown University in 1954, working under the informal supervision of George Gamow himself, who was nearby at George Washington University. But it was not until she joined the Carnegie Institution of Washington in the 1960s that her most transformative work began. At Carnegie, Rubin met an instrument maker named Kent Ford, who had built a remarkably sensitive spectrograph, a device capable of measuring the tiny shifts in the wavelengths of light that reveal how fast a distant object is moving toward or away from the observer. Rubin immediately recognized its potential. She could use Ford's instrument to measure the orbital speeds of individual stars within galaxies with unprecedented precision. She began with the Andromeda Galaxy, Messier 31, our nearest large galactic neighbor, roughly 2.5 million light-years away. According to the physics everyone understood, the stars in a galaxy should behave somewhat like planets in a solar system. In our solar system, the planets closest to the sun orbit fastest because they feel the strongest gravitational pull. Mercury completes an orbit in just 88 Earth days. Neptune, roughly 30 times farther from the sun, takes about 165 years. This decline in orbital speed with increasing distance is called Keplerian motion because it follows the laws that Johannes Kepler derived from observations of planetary orbits in the early 16th century. If most of a galaxy's mass is concentrated in its bright central bulge, where the stars are densest, then stars farther from the center should orbit more slowly, tracing a declining rotation curve. But that is not what Rubin found, not even close. When she plotted the orbital speeds of stars in Andromeda against their distances from the galactic center, the curve did not decline. It stayed flat, stars at the outermost edges of the galaxy. Out where the visible light tapers off into the darkness of intergalactic space, were orbiting just as quickly as stars much closer to the center. According to everything astronomers knew about gravity and visible matter, those outer stars were moving so fast that they should have been flung outward into the void long ago. The galaxy should have torn itself apart billions of years in the past, but there it was, intact and serene, a magnificent spiral, as though some immense, unseen force were holding it together. At first, Rubin suspected an error. She checked Ford's instruments. She repeated the measurements. She and Ford moved on to other spiral galaxies, one after another, with the methodical patience of artists painting the same subject from every possible angle. And the result was always the same. Every galaxy they examined showed the same flat rotation curve. 20 galaxies, then 40, then 60, then more. Each one telling an identical story. The visible matter in a galaxy was just the tip of the iceberg. The vast majority of each galaxy's mass was invisible. Rubin's calculations showed that galaxies must contain at least 5 to 10 times as much unseen mass as visible mass. The luminous stars and gas that we can see occupy only the inner regions of a much larger spherical halo of invisible matter. At least 90% of the mass in galaxies, and therefore in the observable universe, was dark. Rubin had independently and decisively confirmed what Zwicky had proposed 4 decades earlier. But where Zwicky had inferred dark matter from the behavior of entire galaxy clusters, Rubin had found it in the detailed rotation of individual galaxies, a much cleaner, more direct line of evidence. Her data was meticulous, her methodology was airtight, and her results were independently confirmed by radio astronomers who measured the same flat rotation curves using hydrogen gas emissions, extending far beyond the visible disk. The physics behind Rubin's discovery is worth understanding in some detail, because it reveals just how unambiguous the evidence was. In a solar system, the gravitational force on a planet is determined almost entirely by the mass of the central star. Because the star contains more than 99% of the total mass, as you move outward from the star, the gravitational pull weakens and orbital speeds drop. This is why Mercury orbits at roughly 47 kilometers per second, while Neptune crawls along at about 5. The decline follows a precise mathematical relationship derived by Kepler and explained by Newton. Velocity decreases as the square root of the distance from the center. In a galaxy, If most of the mass were concentrated in the bright central bulge, you would expect exactly the same pattern. Stars far from the center should orbit more slowly than stars near the center. The rotation curve should decline, but Rubin's curves were flat. This meant that, as you moved outward from the center of a galaxy, you kept encountering more mass. Not visible mass. The luminous disk of stars and gas ended long before the rotation curve did. The mass had to be invisible, distributed in an extended halo that far exceeded the boundaries of the visible galaxy. The only way to produce a flat rotation curve is if the total mass enclosed within any given orbital radius keeps growing, roughly proportionally to the radius. This implies a spherical halo of dark matter whose density decreases with distance, but whose total enclosed mass keeps rising. This is a genuinely remarkable conclusion. It means that the beautiful spiral galaxy you see in a Hubble photograph, with its graceful arms and brilliant star-forming regions, is actually just the innermost fraction of a much larger, invisible structure. The dark matter halo of a typical galaxy extends perhaps 10 times further than the visible disk and contains perhaps 10 times more mass. The galaxy you see is like the glowing filament inside a light bulb, just the small, bright center of a much larger, darker, and heavier object. Kent Ford, Rubin's collaborator, once reflected on their joint discovery by saying that their spectrograph was like opening a new window on the universe. Through that window, they could see something extraordinary. The entire cosmos was far heavier than it appeared, its mass dominated by an invisible component that no one had anticipated and no one could explain. Rubin was characteristically humble about the implications. She often deflected credit, emphasizing the importance of the data rather than the discoverer. She was also keenly aware of the uncertainties that remained. In a spiral galaxy, the weights are connected to each other. She once explained in an interview, drawing a careful distinction between the gravitational dynamics of galaxies and the simpler Keplerian dynamics of planetary orbits. But the data left no room for doubt about the main conclusion. Galaxies were embedded in massive halos of something invisible. Her work inspired a generation of astronomers to take dark matter seriously. By the mid-1980s, the cold dark matter model had become the standard framework for understanding the formation and evolution of cosmic structures. Theoretical physicists began designing experiments to search for the particles that might make up this invisible mass, and the race to detect dark matter directly had begun. By the early 1980s, the astronomical community had reached a consensus that dark matter was real. It was everywhere, and it dominated the cosmos. Rubin, characteristically modest, often let the data speak for itself. "We have peered into a new world," she once wrote, "and have seen that it is more mysterious and more complex than we had imagined. Still more mysteries of the universe remain hidden. Their discovery awaits the adventurous scientists of the future." Rubin passed away on December 25, 2016, at the age of 88. She was never awarded the Nobel Prize, despite being nominated repeatedly, a fact that many in the scientific community regard as a significant oversight. In 2019, the Large Synoptic Survey Telescope in Chile was renamed the Vera C. Rubin Observatory in her honor, an acknowledgement, even if belated, of the woman who showed humanity that the universe we see is merely a thin, glittering veneer stretched across a vast ocean of invisible matter. After Rubin's work, the evidence for dark matter did not stop accumulating. If anything, it accelerated, coming from directions that Zwicky and Rubin could never have anticipated. One of the most dramatic confirmations came from a cosmic collision 4 billion light-years from Earth. The Bullet Cluster. The Bullet Cluster, formally designated 1E0657-56, is a pair of galaxy clusters that have recently plowed through each other at tremendous speed. It was first detected as a blip of X-rays by NASA's Einstein Observatory in 1992, and subsequent observations revealed its extraordinary nature. When astronomers studied this collision using a battery of instruments, including the Chandra X-ray Observatory, the Hubble Space Telescope, and the Magellan telescopes in Chile, they found something remarkable. The hot gas that fills the space between galaxies in each cluster, which makes up the bulk of the ordinary baryonic matter in a galaxy cluster, had been slowed down and dragged by the collision. This gas interacts through electromagnetic forces. It feels friction, it feels pressure, and when two clouds of it slam together at millions of miles per hour, it gets stuck. In the Chandra images, this slowed-down gas shows up in pink, pooled between the two separating clusters. But the gravitational mass of each cluster, as measured by gravitational lensing of background galaxies, had sailed right through the impact, largely unaffected. Gravitational lensing occurs when a massive object bends the light from more distant objects behind it, distorting their shapes in predictable ways. By measuring these distortions, astronomers can map where the mass actually is. And in the Bullet Cluster, the mass was not where the gas was. The mass was out ahead, in regions represented in blue on the composite images, regions almost devoid of visible matter. This is exactly what you would expect if most of the mass in each cluster were made of dark matter. Ordinary matter interacts with itself through friction, pressure, and electromagnetic forces. Dark matter, by definition, does not. So while the visible gas got stuck in the middle, the dark matter from each cluster passed through the other like two ghosts walking through the same wall, carrying most of the gravitational mass with it. The Bullet Cluster provided what many scientists consider the most compelling direct observational evidence for the existence of dark matter as a distinct substance, separate from ordinary matter. The statistical significance of the separation between the gravitational mass and the visible mass was extraordinarily high, with researchers calculating odds of roughly 1 in a quadrillion that the offset was a fluke. Alternative theories of gravity, like modified Newtonian dynamics, or MOND, struggled mightily to explain why the center of gravity would be located in regions almost empty of visible matter, without invoking some form of invisible mass. Further support came from the cosmic microwave background, the faint afterglow of radiation left over from about 380,000 years after the Big Bang, when the universe had cooled enough for the first atoms to form and light to travel freely through space. This ancient light, first detected accidentally by Arno Penzias and Robert Wilson in 1965, has been mapped in exquisite detail by a series of increasingly sensitive space missions. The COBE satellite in the early 1990s revealed the first large-scale temperature fluctuations. The WMAP mission, launched in 2001, sharpened the picture considerably, and the Planck spacecraft, which operated from 2009 to 2013, produced the most precise map of the CMB ever made. These maps revealed tiny temperature variations across the sky, fluctuations of just a few parts in 100,000. These are the fingerprints of the infant universe, the seeds from which all structure would eventually grow. When scientists analyzed the pattern of these fluctuations, they found that they could only be reproduced by models that included a substantial amount of non-baryonic dark matter. The specific pattern of peaks and troughs in the CMB power spectrum, the relative heights of the acoustic oscillations, all of it depended sensitively on the ratio of dark matter to ordinary matter, and the data demanded roughly 5 times more dark matter than ordinary matter, in perfect agreement with what galaxy rotation curves, galaxy cluster dynamics, and gravitational lensing had independently established. The Planck spacecraft's results, released between 2013 and 2018, pinned down the composition of the universe with spectacular accuracy. Approximately 4.9% ordinary matter, approximately 26.8% dark matter, and approximately 68.3% dark energy. These numbers, consistent across multiple independent measurement techniques spanning billions of years of cosmic history, represent one of the great achievements of modern cosmology. They tell us, with a precision that would have seemed impossible to Zwicky, just how dominated the universe is by what we cannot see. And so, by the turn of the 21st century, the reality of dark matter was established beyond any reasonable doubt, supported by a convergence of evidence from galaxy rotation curves, galaxy cluster dynamics, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, computer simulations of cosmic evolution, and the observed abundances of light elements produced in the first few minutes after the Big Bang. The evidence from gravitational lensing deserves particular attention because it provides what is arguably the most visually dramatic demonstration of dark matter's presence. Einstein's general theory of relativity predicts that massive objects warp the fabric of spacetime around them, causing light rays passing nearby to follow curved paths rather than straight lines. This means that a massive object located between us and a more distant light source can act as a kind of cosmic magnifying glass, bending and distorting the image of the background source. Astronomers call this gravitational lensing, and it comes in several flavors. Strong lensing produces dramatic visual effects. Background galaxies can be stretched into arcs, rings, or even multiple copies of themselves, like funhouse mirror reflections created by the gravity of a foreground galaxy cluster. These distortions are beautiful and unmistakable. Weak lensing is subtler. It produces small, statistical distortions in the shapes of thousands of background galaxies, distortions that can only be detected by averaging over large numbers of sources. But weak lensing is extraordinarily powerful as a tool for mapping the distribution of mass, because it measures total mass directly, whether that mass is luminous or not. By analyzing weak lensing patterns around galaxy clusters, astronomers have mapped the distribution of dark matter with remarkable precision. The results consistently show that the total mass far exceeds the visible mass, and that the dark matter is distributed in broad, diffuse halos that extend well beyond the luminous galaxies. These lensing maps are, in a sense, photographs of dark matter's gravitational influence, images of an invisible substance revealed by its effect on the geometry of space itself. The cosmic microwave background evidence is equally compelling, though it requires a bit more explanation to appreciate. The CMB is essentially a snapshot of the universe at the age of about 380,000 years, when it was roughly 1,000 times smaller and 1,000 times hotter than it is today. At that epoch, the universe transitioned from being an opaque plasma, in which photons were constantly scattering off charged particles, to a transparent gas, in which photons could finally travel freely across space. Those newly liberated photons have been traveling ever since, cooling and redshifting as the universe expanded. Until today, they form a faint microwave glow that pervades the cosmos in every direction. The temperature fluctuations in the CMB arose from density variations in the early universe. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, which compressed the gas, which heated it up. But the heated gas also had higher pressure, which pushed back against gravity, driving the gas outward. This tug-of-war between gravity pulling inward and pressure pushing outward created sound waves, acoustic oscillations that rippled through the early universe like sound waves through air. The pattern of these oscillations is encoded in the CMB temperature map, and it is exquisitely sensitive to the composition of the universe. Here is the key point. Dark matter participates in the gravitational part of these oscillations. It clumps and attracts, but it does not participate in the pressure part, because it does not interact with photons or with the plasma of ordinary matter. This difference between how dark matter and ordinary matter respond to the acoustic oscillations produces a distinctive signature in the CMB power spectrum. The pattern of hot and cold spots at different angular scales. By measuring this signature, cosmologists can separately determine the amount of ordinary matter and the amount of dark matter in the early universe, with a precision of better than 1%, and the answer from the Planck spacecraft's final analysis. The universe contains about 5 times more dark matter than ordinary matter. This ratio, derived from the physics of sound waves in a plasma 380,000 years after the Big Bang, agrees perfectly with the ratio derived from galaxy rotation curves measured in the modern-day universe. 13.8 billion years later, two completely independent methods, measuring different physical processes at different epochs, separated by nearly the entire age of the cosmos, converge on exactly the same answer. That kind of concordance is the hallmark of a genuine physical reality, not a systematic error or a misinterpretation. The question had shifted. It was no longer, does dark matter exist? It was, what is dark matter made of? That question has haunted particle physicists for decades, and of the many candidates that have been proposed, one stands above the rest in popularity, theoretical elegance, and sheer staying power: the WIMP. WIMP stands for Weakly Interacting Massive Particle. The name is partly a playful acronym, deliberately chosen to contrast with another dark matter candidate called MACHOs, or Massive Astrophysical Compact Halo Objects, which proposed that dark matter might be made of ordinary, but non-luminous, objects like brown dwarfs, rogue planets, or old white dwarfs. Gravitational lensing surveys eventually ruled out MACHOs as the primary component of dark matter, but the acronym lives on. WIMPs, despite the unassuming name, represent one of the most carefully reasoned hypotheses in all of modern physics. The idea is elegant in its simplicity. Imagine a particle that is heavier than a proton, perhaps dozens or hundreds of times heavier, but that interacts with ordinary matter only through gravity and the weak nuclear force. The weak force is one of the 4 fundamental forces of nature: responsible for certain types of radioactive decay and for the nuclear reactions that power stars. It operates at incredibly short ranges, only about 1,000th of the diameter of a proton, and is far feebler than either the electromagnetic force or the strong nuclear force that binds protons and neutrons together inside atomic nuclei. A particle that interacts only through gravity, and the weak force would be, for all practical purposes, invisible. It would not absorb, emit, or reflect light. It would not bounce off atoms or molecules in any easily detectable way. It would pass through ordinary matter like a breeze through an open window. Yet, it would be massive enough to move slowly, to clump together under gravity, to form the gravitational scaffolding that shapes galaxies and clusters. In short, it would behave exactly the way dark matter is observed to behave. But why would physicists believe such a particle exists beyond mere convenience? The answer lies in what is sometimes called the WIMP miracle. In the very early universe, when temperatures and energies were unimaginably high, all kinds of particles would have been created and destroyed in a constant frenzy of collisions and annihilations. Matter and antimatter popped in and out of existence. Every conceivable particle species was present. As the universe expanded and cooled, heavier particles began dropping out of this thermal equilibrium. Their creation rates fell as the available energy declined, while their annihilation continued. Eventually, a heavy, weakly interacting particle would reach a point called freeze-out. The universe would have expanded enough that these particles could no longer find each other frequently enough to annihilate. Their numbers would stabilize, and they would persist as cosmic relics, a frozen population of particles drifting through the universe forever after. Here is the remarkable thing. If you calculate the expected relic abundance of these freeze-out particles using nothing but the known strength of the weak force and reasonable assumptions about their mass, somewhere in the range of 10 to several thousand times the mass of a proton, you get a number that is strikingly close to the observed density of dark matter in the universe. Not exactly right, but within the right order of magnitude, a coincidence that physicists find deeply suggestive. The weak force, a force discovered and measured for entirely unrelated reasons in the context of nuclear physics, naturally produces a relic particle population of approximately the right density to explain dark matter. This convergence of the weak interaction scale with the required dark matter density is the WIMP miracle. It suggested that dark matter might not be some exotic, unfathomable substance from beyond the borders of known physics, but rather a natural extension of the physics we already understand, a missing piece of a puzzle that was almost complete. Several theoretical frameworks predict particles that could serve as WIMPs. The most prominent is supersymmetry, often abbreviated as SUSY. Supersymmetry proposes that every known particle has a heavier superpartner. The electron has a selectron, the quark has a squark, the photon has a photino. If supersymmetry is real, then the lightest of these superpartners, the lightest supersymmetric particle, would be stable, would interact through the weak force, and would have a mass in just the right range to explain dark matter. The neutralino, a hypothetical blend of the superpartners of certain force-carrying particles, emerged as the leading WIMP candidate from supersymmetric theories, with predicted masses ranging from roughly 90 to several hundred times the mass of a proton. But WIMPs are not the only game in town. Axions represent another compelling candidate. Originally proposed in 1977 to solve a different problem in particle physics entirely, a puzzle called the strong CP problem. Axions would be extremely light particles with properties quite different from WIMPs, where WIMPs are heavy and slow. Axions would be nearly massless and extraordinarily abundant, forming a pervasive quantum field that fills all of space. Experiments around the world, including the Axion dark matter experiment at the University of Washington, are searching for axions by looking for their predicted conversion into microwave photons in the presence of strong magnetic fields. Then there are more exotic proposals. Primordial black holes, microscopic black holes that may have formed in the chaotic first instance after the Big Bang, have been considered. Self-interacting dark matter models suggest particles that feel an unknown force between them. Fuzzy dark matter proposes ultralight particles with quantum wavelengths billions of times larger than an atom, and some theorists have explored the possibility that dark matter is not a single particle at all, but an entire hidden sector of particles and forces, a shadow universe interleaved with our own. To appreciate why the detection of a new fundamental particle would be so momentous, consider what the standard model of particle physics currently describes. The standard model is, without exaggeration, one of the most successful scientific theories ever devised. It describes 3 of the 4 fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force, and classifies all known elementary particles into a handful of categories. There are 6 quarks, which combine in groups of 3 to form protons and neutrons, and in quark-antiquark pairs to form mesons. There are 6 leptons, the most familiar being the electron, along with its heavier cousins the muon and tau, and 3 types of nearly massless neutrinos. There are force-carrying particles called bosons. The photon mediates electromagnetism, the gluon mediates the strong force, and the W and Z bosons mediate the weak force. And there is the Higgs boson, discovered at the Large Hadron Collider in 2012, which gives mass to other particles through the Higgs mechanism. Together, these particles and forces describe essentially every physical process that has ever been observed in a laboratory, from the burning of a candle, to the decay of radioactive atoms, to the collision of particles at the highest energies achievable by human technology. The standard model has been tested to extraordinary precision, and it has passed every test. But the standard model is incomplete. It does not include gravity. It does not explain why the universe contains more matter than antimatter. It does not predict the masses of particles or the strengths of forces. Those must be measured experimentally and plugged in as free parameters. It does not explain dark energy, and crucially for our story, it does not contain any particle that could serve as dark matter. This last point is worth emphasizing. Despite the standard model's extraordinary explanatory power, it accounts for only about 5% of the mass energy content of the universe. The remaining 95%, the dark matter and dark energy that dominate the cosmos, lies entirely outside its framework. Whatever dark matter is, it must be something new. Something beyond the standard model, something that has never been detected in any particle physics experiment, despite decades of effort. If Totani's signal is real, it would mean that nature contains at least one type of particle that the standard model does not predict. That would be the first discovery of a particle beyond the standard model since. Well, since the standard model was completed in the 1970s. Every particle found since then, including the Higgs boson, was predicted by the existing framework. A genuine dark matter particle would be the first truly unexpected addition, a crack in the wall of our understanding through which entirely new physics might be glimpsed. This is why the stakes are so high. This is why the scrutiny is so intense. And this is why the physics community, despite its excitement, is insisting on extraordinary evidence before it will accept an extraordinary claim. Each candidate makes different predictions about what experiments should find. And for decades, scientists have been building increasingly sensitive machines to test those predictions. If dark matter particles are streaming through the Earth by the billions every second, then in principle, all you need to do to detect one is build a sufficiently sensitive detector and wait for a collision. In practice, this is one of the most difficult experimental challenges in all of science. The problem is that dark matter particles, by definition, barely interact with ordinary matter. A single WIMP passing through a block of material has an astonishingly small probability of bumping into an atomic nucleus. To have any hope of catching even one such interaction, you need a detector that is extraordinarily large, extraordinarily sensitive, and extraordinarily quiet. You need to shield it from every possible source of background noise. From cosmic rays raining down from space, from the natural radioactivity of the rocks and soil around it, from the electronic hum of nearby equipment, even from the thermal vibrations of individual atoms at room temperature. Every stray particle that hits your detector and mimics a dark matter collision is a false alarm that can drown out the faint signal you are looking for. This is why the world's leading dark matter detectors are buried deep underground, in mines and tunnels and caverns, where miles of solid rock absorb the relentless shower of cosmic rays that bombard the Earth's surface. Picture it: a mile beneath the rolling hills of western South Dakota, in tunnels carved by gold miners more than a century ago, in a cavern that once echoed with the ring of pickaxes and the rumble of ore carts, sits one of the most sensitive scientific instruments ever built. The air is cool and still. The rock walls are ancient, more than 1 billion years old. The silence is nearly absolute. And inside a towering cylinder of gleaming steel, surrounded by water and liquid scintillator, and layer upon layer of shielding materials selected for their extraordinary purity, 10 tons of liquid xenon wait in the dark for something invisible to make its presence known. The LUXE-PLIN experiment, known as LZ, sits nearly a mile beneath the surface at the Sanford Underground Research Facility in Lead, South Dakota. The facility is housed in a former gold mine called the Homestake Mine, the same mine where physicist Ray Davis ran his pioneering solar neutrino experiment for decades, work that eventually earned him a Nobel Prize. The mile of rock overhead acts as a natural shield, reducing the flux of cosmic ray muons by a factor of millions compared to the surface. LZ's heart is a cylindrical chamber filled with 10 tons of ultra-pure, ultra-cold liquid xenon. Xenon is an ideal target material for several reasons. Its atoms are heavy, which means they recoil more noticeably when struck by a massive particle. Liquid xenon is transparent to its own scintillation light, so a flash produced by a particle collision can travel through the medium to be detected, and xenon can be purified to extraordinary levels, removing trace radioactive contaminants that would otherwise produce a blinding background of false signals. If a WIMP were to collide with the nucleus of a xenon atom, the collision would cause the nucleus to recoil slightly, depositing a tiny amount of energy. That recoil would produce two detectable signals: a faint flash of ultraviolet scintillation light produced as the recoiling nucleus disturbs its neighbors, and a small stream of electrons knocked free from nearby atoms. An electric field applied across the liquid xenon drifts these electrons to the top of the chamber, where they enter a thin layer of xenon gas and produce a second, larger flash of light called electroluminescence. Both signals are captured by 494 photomultiplier tubes, incredibly sensitive light detectors positioned above and below the xenon volume. By measuring the timing and intensity of the two light flashes, scientists can determine where in the detector the collision occurred, how much energy was deposited, and critically, whether the interaction looks like a nuclear recoil, consistent with a WIMP, or an electronic recoil, more likely from a background gamma ray or electron. Surrounding the central xenon chamber are multiple additional layers of protection. A thin outer region of instrumented xenon helps identify events that occur near the detector walls, where backgrounds are highest. Beyond that, a shell of gadolinium-doped liquid scintillator detects neutrons, which can mimic WIMP signals by scattering off xenon nuclei. And the entire assembly sits inside a large water tank, which provides further shielding against external radiation. LZ is not alone. It represents the latest and most sensitive generation in a lineage of noble gas dark matter detectors. Its predecessors include the Lux experiment, which previously held the title of most sensitive dark matter search, and the Xenon and PandaX collaborations in Italy and China, which have pushed the boundaries using similar technology. Together, these experiments have improved the sensitivity of direct dark matter searches by a factor of over 1 million in the past 2 decades. In December of 2025, the LZ collaboration announced its latest results from 417 live days of data collection. They found no evidence of WIMPs in the mass range they searched, which for the first time extended down to just 3 times the mass of a proton. But they set the tightest constraints yet on how strongly WIMPs can interact with ordinary matter. They also achieved a remarkable milestone: the detection of neutrinos from the sun's core through a process called coherent elastic neutrino nucleus scattering. A signal so faint it had never been conclusively detected in a xenon experiment before. This detection of solar neutrinos, while not dark matter itself, demonstrated that LZ sensitivity is approaching the so-called neutrino fog, the point at which solar neutrino interactions become an irreducible background that future dark matter searches will have to contend with. The null results from direct detection experiments do not mean WIMPs do not exist. They may interact even more weakly than the simplest models predicted, or have masses outside the ranges currently accessible, but they have squeezed the available parameter space significantly, ruling out the most optimistic theoretical scenarios and pushing the dark matter search into territory that requires ever more sensitive instruments. The history of direct dark matter detection experiments is itself a remarkable story of human ingenuity and perseverance. The first generation of experiments in the 1980s and early 90s used relatively small detectors and achieved sensitivities that, by today's standards, seem almost quaint, but they established the basic principles and technologies that all subsequent experiments would build upon. One of the earliest approaches used germanium crystals cooled to temperatures just above absolute zero. When a WIMP struck a germanium nucleus, the recoil would produce a tiny amount of heat and a small electrical signal. By measuring both, researchers could distinguish between different types of particle interactions. The CDMS experiment, the cryogenic dark matter search, used this technique at the Soudan mine in Minnesota, setting world-leading sensitivity limits for years. But the field was rapidly transformed by the development of noble liquid detectors, first using liquid argon, and then, increasingly, liquid xenon. Xenon proved to be the superior target material for WIMP searches. Its high atomic mass meant that nuclear recoils from WIMP collisions deposited more energy, making them easier to detect. Its excellent scintillation properties meant that even tiny energy deposits produced detectable flashes of light, and its ability to be purified to extraordinary levels meant that internal radioactive backgrounds could be suppressed to almost nothing. The progression of xenon experiments reads like a relentless march toward greater sensitivity. ZEPLIN, a pioneering experiment at the Balby Underground Laboratory in England, demonstrated the basic dual-phase xenon technique. Xenon 10 at Gran Sasso in Italy, using about 15 kilograms of liquid xenon, set new limits in the mid-2000s. Xenon 100 with 62 kilograms pushed further. Lux, at the Sanford Underground Research Facility, raised the bar again with 300 kilograms. Xenon 1T, with 2 tons, achieved sensitivities that would have seemed impossible a decade earlier. And now LZ, with 10 tons, is probing interaction rates so tiny that only a few events per year per ton of xenon would be expected, even if WIMPs exist with the properties predicted by the most favorable models. Each generation of experiment has been roughly 10 times more sensitive than the last, and each has reported the same result: no signal above background. The constraints have grown ever tighter, excluding larger and larger swaths of the theoretical parameter space in which WIMPs might reside. But still, significant territory remains unexplored. The ongoing LZ experiment, which plans to collect data through 2028, will probe the most promising remaining WIMP models. If it too finds nothing, the attention of the field may shift more decisively toward alternative candidates like axions, or toward entirely new ideas that have not yet been conceived. Meanwhile, a different kind of dark matter experiment operates not underground, but at the highest energies humans have ever achieved. The Large Hadron Collider at CERN, the European Organization for Nuclear Research, near Geneva, Switzerland, smashes protons together at energies of 13 trillion electron volts. If WIMPs exist with masses in the range of a few hundred times the mass of a proton, they could, in principle, be created in these collisions. Because WIMPs would not interact with the detectors surrounding the collision point, they would escape unnoticed, carrying away energy and momentum. Scientists would infer their existence from the missing energy in the collision products, a deficit that could not be accounted for by any known particles. So far, the LHC has not found any evidence of WIMPs or of supersymmetric particles more generally. The absence of supersymmetry at the LHC has been one of the most significant null results in recent particle physics, and it has caused some theorists to question whether WIMPs remain viable dark matter candidates. But the LHC can only probe certain mass ranges and interaction strengths, and a vast territory of WIMP parameter space lies beyond its reach. The search at CERN continues, with upgrades to the LHC planned that will increase its collision energy and its ability to detect rare processes. And so, even as direct detection experiments continued their patient vigil underground, other scientists were looking for dark matter from a different vantage point, not beneath the Earth, but above it from orbit, using a telescope that sees the universe in gamma rays. On June 11, 2008, a Delta II heavy rocket lifted off from Cape Canaveral, carrying into low Earth orbit a spacecraft that would become one of the most productive observatories in the history of astrophysics. It was a moment that few outside the gamma-ray astronomy community noticed at the time, but its consequences would ripple through physics for decades. Originally called the Gamma-ray Large Area Space Telescope, it was renamed within months in honor of Enrico Fermi, the Italian-American physicist who laid the groundwork for the study of nuclear reactions, particle physics, and the very kinds of high-energy phenomena the telescope was designed to observe. Fermi, who won the Nobel Prize in 1938 and later helped build the first nuclear reactor, would surely have appreciated the ambition of the mission that now bore his name, to survey the entire universe in its most energetic light, searching for clues about the most extreme processes in nature, from the jets of supermassive black holes to the annihilation of dark matter particles. The Fermi Gamma-ray Space Telescope has been watching the sky continuously for more than 17 years now, circling the Earth every 96 minutes at an altitude of roughly 350 miles. And its discoveries have reshaped our understanding of the high-energy universe. It has detected over 300 gamma-ray pulsars. It has observed gamma-ray bursts from the most distant reaches of the cosmos. It has detected the electromagnetic counterpart of a gravitational wave event, a merger of two neutron stars observed simultaneously in both gravitational waves and gamma rays, opening the era of multi-messenger astronomy. It has revealed the Fermi bubbles, two enormous structures of gamma-ray emission extending roughly 25,000 light-years above and below the plane of the Milky Way, likely produced by an outburst from the supermassive black hole at our galaxy's center. But one of its most important scientific goals from the very beginning was the indirect search for dark matter. The logic is compelling. If dark matter is made of WIMPs, and if WIMPs occasionally annihilate when they collide with each other, then those annihilation events should produce a cascade of ordinary particles, including gamma-ray photons. The energy of those gamma rays is tied to the mass of the WIMP. A heavier WIMP produces higher energy gamma rays, and the signal should be strongest where dark matter is densest. In our galaxy, dark matter is thought to be concentrated in a massive halo centered on the galactic core, with the density increasing toward the center. That makes the region around the galactic center the prime hunting ground for WIMP annihilation signals. The Fermi Telescope's Large Area Telescope is exquisitely suited for this search. It scans the entire sky every 3 hours, detecting gamma-ray photons with energies from about 20 million electron volts up to more than 300 billion electron volts. Over 15+ years of operation, it has accumulated a dataset of staggering size and statistical power, enabling analyses that would have been impossible with even a few years of data. But the search has been anything but straightforward. As early as 2009, just 1 year after Fermi launched, scientists noticed an unexplained excess of gamma rays emanating from the galactic center. This galactic center excess sparked years of excited debate. Some researchers argued it was the long-awaited signature of dark matter annihilation. Others contended it was more likely caused by a large population of unresolved millisecond pulsars, rapidly spinning neutron stars that are known gamma-ray emitters, but are individually too faint to detect at the distance of the galactic center. After more than 16 years of analysis and counter-analysis, the community has never reached a consensus. The galactic center is simply too crowded, too complicated, too full of competing gamma-ray sources to allow a clean extraction of any dark matter signal. And that brings us, finally, to the new study that shook the physics world in late 2025. Professor Tomonori Totani of the University of Tokyo took a different approach. Rather than staring into the chaotic heart of the galaxy, he looked above and below it, into the calmer, emptier region of the galactic halo. Dark matter should be present there too, if the standard halo model is correct, just at lower densities. The signal would be fainter, but the background noise would also be dramatically reduced. It was a trade-off, harder to see, but cleaner to interpret. To detect such a faint signal, Totani needed every photon he could get. He used the full 15 years of Fermi-Lat data, one of the most comprehensive gamma-ray datasets ever assembled. He carefully modeled and subtracted every known source of gamma-ray emission in the halo region: the Fermi bubbles, cataloged point sources, the diffuse glow produced by cosmic rays interacting with interstellar gas and radiation fields. This process of source subtraction is painstaking and sensitive to assumptions. Different models of the background can yield different residuals. And it is here, in the details of how the subtraction is performed, that much of the subsequent debate would focus. But after all known components had been removed, what remained was a signal. A diffuse glow of gamma rays, concentrated toward the galactic center and fading with distance, peaking at an energy of about 20 gigaelectronvolts. The spatial distribution of this excess, its shape and extent, matched the profile expected for dark matter annihilation in a galactic halo. The energy spectrum, the way the intensity varied with photon energy, rose steeply from low energies, peaked sharply near 20 gigaelectronvolts, and fell off at higher energies, a shape that closely matched theoretical predictions for WIMPs annihilating and producing pairs of bottom quarks, or W bosons. The implied WIMP mass was approximately 500 times the mass of a proton, and the inferred annihilation rate fell within the range of theoretical expectations. To fully appreciate the difficulty of Totani's analysis, it helps to understand just how complex the gamma-ray sky actually is. When the Fermi telescope looks toward the center of our galaxy, it sees a riot of gamma-ray sources. Pulsars, both young and recycled millisecond pulsars, emit beams of gamma radiation that sweep through space like lighthouse beacons. Supernova remnants, the expanding shells of debris left behind when massive stars explode, accelerate particles to enormous energies, producing gamma rays when those particles interact with surrounding gas and radiation fields. Binary star systems, in which a compact object like a neutron star or black hole strips matter from a companion star, can produce gamma-ray jets, and the entire plane of the galaxy is bathed in a diffuse gamma-ray glow produced by cosmic rays, high-energy protons and electrons that were accelerated in supernova shockwaves and now careen through interstellar space, colliding with gas atoms and producing secondary gamma-ray photons. All of these sources must be modeled and subtracted before any residual signal can be attributed to dark matter. The accuracy of the final result depends critically on the accuracy of these background models, and this is where the devil lurks in the details. Different research groups have used different approaches to model the galactic gamma-ray foreground, and they have sometimes arrived at very different conclusions about whether an excess exists. Some models absorb the excess into their description of the astrophysical backgrounds, effectively explaining it away. Others leave a residual that looks tantalizingly like dark matter. The outcome can depend on assumptions about the distribution of cosmic ray sources, the density of interstellar gas, the population of unresolved pulsars, and dozens of other parameters, each of which carries its own uncertainty. Totani's approach of focusing on the halo, away from the densest concentration of astrophysical sources, is a clever strategy to mitigate these difficulties. But even the halo is not a perfect laboratory. The Fermi bubbles, two enormous lobes of gamma-ray emission, extending about 25,000 light-years above and below the galactic center, must be carefully modeled and removed. Inverse Compton scattering, in which high-energy electrons boost low-energy photons to gamma-ray energies, produces a diffuse glow throughout the halo. And there may be sources of gamma-ray emission in the halo that are not yet fully understood or cataloged. Totani contends that the signal he found cannot be easily explained by any of these known sources, that its spatial distribution is spherically symmetric in a way that astrophysical sources are not, and that its energy spectrum has a distinctive peaked shape that does not match any known gamma-ray production mechanism. These are strong arguments. But other experts have noted that the history of Fermi data analysis is filled with cases where initially promising signals were later attributed to imperfectly modeled backgrounds. The standard of proof for a discovery of this magnitude is very high, and understandably so. The specific energy of 20 gigaelectronvolts, where Totani's signal peaks, is itself a piece of the puzzle. In WIMP annihilation models, the energy spectrum of the resulting gamma rays depends on several factors: the mass of the WIMP, the specific particles produced when the WIMPs annihilate, and the subsequent cascade of decays and interactions as those particles lose energy and produce photons. When two WIMPs with a combined mass of roughly 1,000 proton masses, 500 each, annihilate, they could produce a variety of standard model particles. Totani's analysis found that the observed energy spectrum best matches two scenarios: annihilation into pairs of bottom quarks, the heavy cousin of the down quark, or pairs of W bosons, the force carriers of the weak nuclear force. Both channels would produce a shower of secondary particles that would ultimately yield gamma-ray photons with a characteristic energy distribution, peaking below the WIMP mass and extending down to lower energies. The bottom quark channel is particularly interesting because bottom quarks are among the heaviest fermions in the standard model, and their production in WIMP annihilation is a common prediction of many supersymmetric models. The W boson channel is similarly well motivated, since WIMPs that interact through the weak force would naturally couple to W bosons. The fact that the observed spectrum is well fit by these specific annihilation channels, rather than being a featureless blob of excess emission, is another point in favor of the dark matter interpretation. Astrophysical sources tend to produce power law spectra, smooth distributions of gamma-ray energies that decrease steadily with increasing energy. The peaked, bump-like spectrum that Totani reports is more difficult to explain with known astrophysical processes. Though not impossible, it is worth noting that the previous galactic center excess, the one debated since 2009, peaked at a lower energy of about 2 to 3 gigaelectronvolts, corresponding to a lighter WIMP mass of roughly 30 to 50 proton masses. Totani's halo excess peaks at a significantly higher energy and implies a much heavier WIMP. These are different signals, not the same one viewed from different angles. They would require different dark matter particles to explain them, which could be evidence against a dark matter interpretation, since it is simpler to assume one type of dark matter, or could indicate that the universe contains more than one species of dark matter particle. One interesting aspect of Totani's finding is that the new halo excess and the previously identified galactic center excess appear to have different spatial distributions and different energy spectra. If both were caused by the same population of pulsars, for example, you might expect them to share similar characteristics. The fact that they look different could be evidence that they have different origins, which would support the idea that at least one of them might be from dark matter. Alternatively, it could simply reflect the complexity of the astrophysical environment, with different populations of sources dominating in different regions. Totani published his paper as a single author, which is unusual in modern astrophysics, where large collaborations are the norm. Some observers have noted that this means the analysis has not been subject to the internal checks and scrutiny that typically occur within a large research group before publication. This does not mean the work is wrong. Many important discoveries have come from individual researchers working independently. But it does mean that external verification by independent groups is especially important to understand why the center of our galaxy is such a natural place to look for dark matter signals. You need to visualize the structure of a dark matter halo. Imagine a vast, roughly spherical cloud of invisible particles centered on the galactic core, densest at the very center, and thinning smoothly as you move outward. The Milky Way's dark matter halo is believed to extend at least 300,000 light-years from the galactic center, roughly 6 times the diameter of the visible galaxy. At its center, the density is highest, and density matters enormously for annihilation. The rate at which 2 WIMPs annihilate depends on the square of the local dark matter density. Double the density, and you quadruple the annihilation rate. This means that the signal from WIMP annihilation should be dramatically concentrated toward the galactic center, creating a gamma-ray glow that fades with distance. This density profile is described mathematically by what physicists call an NFW profile, named after the 3 scientists, Navarro, Frank, and White, who derived it from computer simulations of dark matter structure formation in the 1990s. The NFW profile predicts that dark matter density rises steeply toward the center of a halo and falls off more steeply at larger distances. If dark matter annihilation produces gamma rays, their brightness, as a function of angle from the galactic center, should trace this density squared profile. The fact that Totani's excess follows this expected profile is one of the strongest arguments in favor of a dark matter interpretation. Since astrophysical sources of gamma rays tend to follow the distribution of visible matter concentrated in the galactic disk, rather than in a spherical halo, a genuinely spherically symmetric signal that tracks the dark matter halo would be difficult to produce from any known astrophysical process. But this argument, while suggestive, is not conclusive. Different background models can alter the apparent shape of the residual signal, and certain combinations of astrophysical sources could, in principle, mimic a halo-like distribution. This is precisely why dwarf galaxies are so critical as an independent cross-check. Dwarf galaxies have their own dark matter halos, independent of the Milky Way's. If the same gamma-ray signature appears in multiple dwarf galaxies, with the same energy spectrum and the same density-dependent spatial profile, the case for dark matter would become extremely strong. No known population of astrophysical sources could produce the same signal, at the same energy, in the same spatial pattern, across multiple independent systems with wildly different stellar populations and environments. Totani described his reaction with disarming candor. The discovery, he said, felt like winning the lottery. He was initially skeptical when he first noticed the anomalous signal, but as he checked his analysis meticulously, running and rerunning the calculations, his confidence grew. When he became satisfied that the signal was robust, he got goosebumps. He published the result in the Journal of Cosmology and Astroparticle Physics on November 26, 2025, under the title 20 GeV Halo-like Excess of the Galactic Diffuse Emission and Implications for Dark Matter Annihilation. If correct, he stated, it would mark the first time humanity has seen dark matter, and it would mean that dark matter is a new particle not included in the current standard model of particle physics. The reaction from the broader scientific community was, to put it diplomatically, cautious. Several prominent experts expressed reservations. Jan Conrad, a professor of astroparticle physics at Stockholm University and an independent expert in gamma-ray dark matter searches, pointed out that making confident claims from Fermi data is notoriously difficult. The astrophysical backgrounds are uncertain. The galactic environment is complex, and previous claims of dark matter signals from Fermi, including the long-debated galactic center, excess, remain unresolved after 16 years of study. Stacy McGaugh, an astrophysicist at Case Western Reserve University, noted that a similar excess of gamma rays was identified as early as 2009, and subsequent analyses have failed to settle whether it is connected to dark matter. He expressed concern about the methodology, pointing out that Totani used data from a computer simulation to model the dark matter distribution in the galaxy, rather than relying on actual observational measurements that exist. Different assumptions about the dark matter density profile can significantly affect the results. David Kaplan, a professor at Johns Hopkins University, raised a broader epistemological point. Scientists do not yet know all the things that can produce gamma rays in the universe. Any claim that a gamma ray excess must come from dark matter necessarily depends on having correctly identified and subtracted every other possible source. And that is a very high bar to clear. Renee H. Lozak, a cosmologist at the University of Toronto, noted that the paper, as a single-author work, had not yet been scrutinized by independent teams and appeared to skip over some of the more sophisticated background modeling approaches that other Fermi analyses have employed. The history of the galactic center excess is itself a cautionary tale about the difficulty of claiming discovery in gamma-ray astronomy in 2009, just a year after the Fermi telescope began operations. Astronomer Dan Hooper and physicist Lisa Goodenough published a paper arguing that they had found an excess of gamma rays at energies of a few gigaelectronvolts emanating from the inner region of our galaxy. The signal appeared consistent with WIMP dark matter, with a mass of roughly 30 to 50 times the mass of a proton, annihilating through bottom quark channels. The paper generated enormous excitement. Over the following years, multiple independent groups analyzed the Fermi data using different techniques and different background models. Some confirmed the excess. Others attributed it to unresolved populations of millisecond pulsars, rapidly spinning neutron stars that emit gamma rays, but are individually too faint to be detected at the distance of the galactic center. Still others argued that the excess was an artifact of imperfect modeling of the galactic diffuse emission, the broad gamma-ray glow produced by cosmic rays interacting with interstellar gas. The debate raged for over a decade. Papers were published arguing for dark matter. Papers were published arguing for pulsars. Papers were published arguing for neither, or for both, or for entirely different explanations. Conferences were held, workshops were organized, and at the end of it all, the question remained unresolved. This history looms large over Totani's new claim. Many of the same issues that made the galactic center excess so difficult to interpret, uncertain backgrounds, complex astrophysical environments, the challenge of distinguishing a genuine new signal from an imperfectly modeled known one, apply to the halo excess as well. Totani's choice to focus on the halo rather than the galactic center itself mitigates some of these issues, since the halo is a simpler environment with fewer competing gamma-ray sources. But the fundamental challenge remains the same. How do you prove that a faint glow of gamma rays is caused by an entirely new physical process, rather than by some combination of known ones that has not yet been correctly modeled? The answer, ultimately, is convergent evidence. A single gamma-ray excess, no matter how suggestive, will not convince the skeptics. But a gamma-ray excess in the galactic halo, combined with the same signal from dwarf galaxies, combined with a consistent detection in an underground experiment, combined with a compatible measurement from a cosmic ray observatory, that combination would be very difficult to explain away. And it is that kind of multifaceted confirmation that the field is now working toward. These criticisms are not dismissals. They are the normal, essential functioning of the scientific process. A claim this extraordinary demands extraordinary scrutiny, and it is precisely because the stakes are so high that the bar for acceptance must be set high. The history of physics is full of signals that looked convincing at first, and later turned out to be artifacts of imperfect background subtraction, instrumental effects, or unmodeled sources. But Totani himself appears well aware of all this. He has openly called for independent verification of his results by other research groups using different analytical methods, and he has identified the single most important next step that could confirm or refute his claim: dwarf galaxies. Dwarf galaxies are small, faint galaxies that orbit within the Milky Way's dark matter halo. They are believed to be extraordinarily rich in dark matter, with dark matter outweighing visible matter by factors of hundreds or even thousands. Crucially, they are much simpler environments than the galactic center or even the galactic halo. They contain far fewer stars, far fewer pulsars, far fewer of the astrophysical sources that produce confusing gamma-ray backgrounds. If the same 20 gigaelectronvolt gamma-ray excess that Totani found in the Milky Way's halo also appears in dwarf galaxies, it would be extremely difficult to explain by anything other than dark matter annihilation. Other paths to confirmation exist. Underground direct detection experiments like LZ could potentially detect WIMPs with masses in the range that Totani's analysis suggests. If LZ, during its planned operation through 2028, were to record a signal consistent with a WIMP of roughly 500 proton masses, the convergence of an underground detection and a gamma-ray signal would be overwhelming. As Jan Conrad observed, seeing a consistent signal in an underground detector would be a very strong argument, because those experiments operate in a much cleaner, better controlled environment. The next generation Cherenkov Telescope Array Observatory, currently under construction at sites in Chile and the Canary Islands, will be the most sensitive ground-based gamma-ray observatory ever built. When it comes online, it will be able to scrutinize the halo signal in far more detail, with better angular resolution and energy sensitivity than the Fermi telescope. If the signal is real, the CTAO should be able to confirm it with greater statistical significance. If the signal is an artifact, the CTAO should be able to reveal that too, and the Fermi telescope itself continues to operate, its instruments still in good health after more than 17 years in orbit, continuing to accumulate data. Every additional year of observations either strengthens a genuine signal or dilutes a false one. The coming years will be decisive for dark matter research, regardless of whether Totani's signal holds up. The LZ experiment has been collecting data since 2022 and plans to continue through 2028, ultimately accumulating more than 1,000 live days of exposure. With each passing month, its sensitivity improves, probing ever smaller interaction cross-sections and extending its reach to dark matter masses that were previously inaccessible. If WIMPs exist with the properties Totani's analysis suggests, a mass of about 500 proton masses, LZ's full dataset should be able to either detect them or rule them out at that mass, provided their interaction with ordinary matter is not vanishingly small. The XLZD Rare Event Observatory, a proposed next-generation experiment that would combine technology from LZ, Xenon, and other collaborations, would be even more ambitious, using 40 or more tons of liquid xenon. XLZD would push the sensitivity frontier further than any experiment before it, probing the deepest reaches of the WIMP parameter space before hitting the irreducible background of coherent neutrino nucleus scattering, the so-called neutrino floor, beyond which solar, atmospheric, and supernova neutrinos mimic the dark matter signal so perfectly that distinguishing them becomes a separate challenge. On the gamma-ray front, the Cherenkov Telescope Array Observatory will transform our ability to study the galactic halo and dwarf galaxies. Unlike the Fermi satellite, which detects individual gamma-ray photons from space, the CTAO will detect the faint flashes of blue light, Cherenkov radiation, produced when gamma rays strike Earth's atmosphere and create cascading showers of particles. By using arrays of dozens of telescopes spread across large areas, the CTAO will achieve an order of magnitude improvement in sensitivity over existing ground-based gamma-ray observatories, with better energy resolution and angular resolution as well. If Totani's 20 gigaelectronvolt halo signal is real, the CTAO should be able to map it in fine detail, measuring its spatial profile, energy spectrum, and variability with far greater precision than the Fermi telescope can achieve. If the signal is not real, the CTAO should be able to demonstrate conclusively that no excess exists at that energy. Either way, the answer will advance our understanding. And then there are the indirect approaches that do not involve gamma rays at all. The IceCube Neutrino Observatory at the South Pole, a cubic kilometer of Antarctic ice instrumented with thousands of light sensors, can search for high-energy neutrinos produced by WIMP annihilation in the Sun or the galactic center. The Alpha Magnetic Spectrometer, mounted on the International Space Station, measures cosmic ray positrons and antiprotons, which could be produced by WIMP annihilation in the galactic halo. Each of these experiments provides an independent window on dark matter, and a positive signal in any one of them would lend powerful support to signals seen in the others. The beauty of the multi-messenger approach to dark matter is that each detection method has different strengths and different systematic uncertainties. A gamma-ray signal from the galactic halo, confirmed by a neutrino signal from the galactic center, confirmed by a nuclear recoil in an underground xenon detector, confirmed by an excess of antiprotons in cosmic rays. That kind of convergence from multiple independent experiments using different technologies and different physical processes would constitute overwhelming evidence for the existence and properties of dark matter particles. It would be the scientific equivalent of multiple eyewitnesses independently describing the same event. And it would, after 92 years, finally close the book on one of the greatest mysteries in the history of science, or possibly open an even bigger one. So where does this leave us? Where does it leave the nearly century-long quest to understand the invisible universe? The honest answer is balanced on a knife's edge. The scientific community now finds itself in a familiar but exhilarating position, poised between a potentially historic discovery and the ever-present possibility of a false alarm. The experience is not unlike the months that preceded the confirmation of the Higgs boson at the Large Hadron Collider in 2012, when physicists had a signal that looked right, at the right mass, with the right properties, but could not yet rule out the possibility that it was a statistical fluctuation. In that case, patience and additional data ultimately confirmed the discovery. Dark matter physicists are hoping for the same outcome, but they know from bitter experience that the universe does not always cooperate. What makes this moment different from previous dark matter claims is the specificity of the prediction. Totani is not simply reporting an unexplained excess of gamma rays. He is reporting an excess with a particular energy spectrum that matches a particular WIMP mass, annihilating through particular standard model channels, distributed in a particular spatial pattern that matches the predicted dark matter halo profile. Each of these elements is independently testable, and each provides an opportunity for the claim to either strengthen or collapse. A signal that has this many independently verifiable characteristics is, in principle, much more robust than a generic excess, but it also provides more ways for the claim to fail if any of those characteristics turn out to be wrong. If Tominori Totani is right, the implications cascade through every branch of physics and astronomy. It would mean that dark matter is indeed made of WIMPs, particles roughly 500 times the mass of a proton that interact through the weak force and annihilate into showers of ordinary particles when they collide. It would mean that the invisible scaffolding that holds galaxies together, the cosmic web that connects galaxy clusters across billions of light years, is made of a specific, identifiable particle, a new fundamental building block of nature, hiding in plain sight for 92 years. It would vindicate decades of theoretical work. It would provide a concrete target for accelerator experiments at CERN's Large Hadron Collider, where physicists could attempt to create WIMPs in high-energy collisions. It would open an entirely new field of dark matter astronomy, in which scientists study the distribution and behavior of dark matter by observing its annihilation products, turning an invisible substance into something measurable and mappable. It would transform our understanding of particle physics, cosmology, and the fundamental architecture of reality. But if Totani is wrong, that too would carry meaning. Every null result, every false alarm, every signal that turns out to be something other than dark matter narrows the range of possibilities. It tells us that dark matter does not behave in the way that signal suggested. It pushes scientists to develop better models, better detectors, better analytical techniques. It reminds us that the universe is under no obligation to be easily understood, and that the greatest mysteries often resist resolution for precisely the reasons that make them so important. Consider for a moment just how far we have come. In 1933, Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast and proposed, to general indifference, that invisible matter must be responsible. In the 1970s, Vera Rubin measured the rotation curves of spiral galaxies and proved, beyond reasonable doubt, that dark matter pervaded the cosmos. In 2006, the Bullet cluster showed dark matter and ordinary matter physically separated in the aftermath of a collision, providing the closest thing to a direct portrait of dark matter's gravitational influence. A cosmic smoking gun that convinced even some of the most hardened skeptics. In 2008, the Fermi telescope launched and began scanning the gamma-ray sky, adding a powerful new tool to the dark matter hunter's arsenal. In 2025, a single astronomer in Tokyo sifted through 15 years of that data and found a signal that looked like the thing everyone had been searching for. Each step brought us closer. Each step sharpened the question. And now we wait. The universe has given us a tantalizing hint, a faint whisper of gamma radiation from the darkness between the stars. It could be the breakthrough that every dark matter physicist has dreamed of for decades. It could be the moment that everything changes, the moment that the invisible majority of our cosmos finally reveals its identity. Or it could be another lesson in the universe's capacity to fool us, to dangle promises just out of reach, to remind us how much we still do not know. We wait for other teams to analyze the data independently. We wait for the Cherenkov telescope array to come online and turn its mirrors toward the galactic halo. We wait for LZ and its successors to continue their silent vigil, a mile underground in a former gold mine, watching for the faintest flash of light from a single xenon nucleus nudged by an invisible particle. We wait for the universe to reveal its secrets at its own pace, which is rarely the pace that impatient humans would prefer. The universe, after all, has kept this secret for 13.8 billion years. It may not surrender easily. But the fact that we are even asking the question, that we have built space telescopes and underground detectors and particle accelerators, specifically to pursue an invisible substance that has never been directly observed, is itself a testament to something remarkable about our species. We refuse to accept that the invisible is unknowable. We refuse to believe that just because something cannot be seen, it cannot eventually be understood. Nearly a century ago, a cantankerous Swiss astronomer looked at a cluster of galaxies and noticed that the math did not work unless something invisible was there. He was called eccentric. He was ignored. He was right. Today, a faint glow of gamma rays in the halo of our galaxy may be telling us the same story in a different language, the language of photons born from the annihilation of particles that no human hand has ever held, no microscope has ever imaged, no accelerator has ever confirmed. Particles that may constitute the overwhelming majority of all matter in the cosmos. Particles that built the cosmic web, sculpted the galaxies, and allowed, through their patient gravitational labor over billions of years, for a small blue planet to form in a quiet arm of an ordinary spiral galaxy, where curious beings eventually evolved the capacity to look up at the night sky and wonder what else might be out there, hiding in the dark. We may be closer to an answer than we have ever been. Or we may be staring at another shimmer in the cosmic desert, another mirage born of our own longing for understanding. Either way, the telescopes keep watching, the detectors keep listening, the data keep accumulating. And somewhere out there, passing through you this very moment, silent and invisible, and perhaps forever unknowable, or perhaps, just perhaps, finally on the verge of being caught, the dark matter streams on. What would it mean for dark matter to be a WIMP with a mass of roughly 500 proton masses? If confirmed, this particular mass would place the particle well within the range that supersymmetric theories predict for the neutralino, though it would also be consistent with other theoretical frameworks. It would be heavy enough to have been produced in the early universe and to have frozen out at the right density. It would be within the mass range that the next generation of underground detectors and ground-based telescopes are designed to probe. It would also raise new questions. If dark matter is a single type of WIMP, why has it been so difficult to detect directly? The null results from LZ, Xenon, and Pandex suggest that its interaction cross-section with ordinary matter is extremely small, possibly smaller than the simplest supersymmetric models predicted. How can a particle interact strongly enough with itself to produce detectable gamma rays through annihilation, yet interact so weakly with ordinary matter that it escapes detection in the most sensitive laboratories ever built? There are theoretical frameworks that can accommodate this. In some models, WIMPs interact preferentially with each other rather than with ordinary nuclei. The annihilation cross-section, which determines how often two WIMPs destroy each other, can be much larger than the scattering cross-section, which determines how often a WIMP bounces off a xenon atom. In these models, a strong gamma-ray annihilation signal and a null result in direct detection experiments are perfectly compatible. And there is another tantalizing possibility. Even if Totani's 500 proton mass WIMPs turn out to be real, they might not be the whole story. Dark matter could be made of multiple types of particles, just as ordinary matter is made of protons, neutrons, and electrons. The WIMPs that annihilate and produce gamma rays might be one component of a richer dark sector that includes other particles with different masses and different properties. If dark matter is not a single substance, but a diverse ecosystem of invisible particles, then the journey of discovery that began with Fritz Zwicky in 1933 may only be in its opening chapters. In physics, every answered question tends to spawn a dozen new ones. The discovery of dark matter particles would not be the end of the story. It would be the beginning of an entirely new field of inquiry, one that could keep scientists busy for centuries. And that, perhaps, is the most exciting prospect of all. We live in a universe that is mostly invisible. We are surrounded by matter that we cannot see, cannot touch, cannot taste, and cannot hear. It passes through us constantly, interacts with us only through the gentlest of gravitational whispers, and yet it outweighs everything we have ever known by a factor of 5. It built the galaxies. It sculpted the cosmic web. It made the stars that forged the elements in our bodies. And after 92 years of searching, we may, at last, be on the threshold of seeing it for the very first time. There is something profoundly humbling about the realization that most of the matter in the universe is fundamentally alien to us. We are made of protons, neutrons, and electrons. Our bodies, our planet, our sun, the ground beneath our feet, the air in our lungs. All of it is built from ingredients that make up roughly 5% of the cosmos. The other 95% is made of something else entirely. Something that does not interact with light, does not form atoms, and as far as we know, does not form structures more complex than vast, diffuse halos of particles drifting through the void. If you could somehow gather up all the atoms in the observable universe, every hydrogen atom in every star, every oxygen atom in every glass of water on every planet, every carbon atom in every living thing that has ever existed, and put them on one side of a cosmic scale, and then put all the dark matter on the other side, the dark matter would outweigh everything else by a factor of 5. For every kilogram of the stuff that makes up you and me, and everything we have ever known, there are 5 kilograms of something utterly invisible, something intangible, flowing through the cosmos in silent rivers that we can only trace by their gravitational wake. We are not made of the dominant form of matter in the universe. We are the exception, not the rule. The cosmos is overwhelmingly composed of something foreign to our experience, something that neither our senses nor our instruments could directly perceive until, perhaps, now. And yet, despite being so alien, dark matter is not separate from us. It is intimately connected to our existence. Without dark matter, the gravitational seeds that grew into galaxies would never have formed. Without dark matter, there would be no Milky Way, no solar system, no Earth. Without dark matter, there would be no stars to forge the carbon in our DNA or the oxygen in our lungs. In a very real sense, we owe our existence to the very substance that hides from us. That irony, the idea that we were built by something we cannot see and may never fully understand, is one of the most beautiful and unsettling truths in all of science. Whatever the final verdict on Totani's signal, one thing is certain: the search for dark matter is one of the great scientific adventures of our time. And the fact that we are capable of pursuing it, of building machines sensitive enough to detect a single invisible particle striking a single atom a mile underground, of launching telescopes into space that can map the gamma-ray glow of annihilating particles at the center of our galaxy. That is a testament to the extraordinary power and ambition of the human mind. The universe does not owe us its secrets, but we keep asking, keep searching, keep building, and keep hoping. And sometimes, if we are very patient and very clever, the universe answers back. If you enjoyed this journey through the invisible universe, please take a moment to hit the like button and subscribe to the channel. Leave a comment and tell us what you think. Is this the real deal? Has dark matter, after nearly a century of hiding, finally been seen? Or are we reading too much into a faint signal from a noisy cosmos? We would love to hear your thoughts. Drop a comment below. Thanks for watching, and we will see you next time.